For nearly a century, astronomers have hunted for the largest star in the known universe, a title that has been passed between giants as telescopes and measurement techniques improved. Today, we dive into the most dramatic showdown in modern astronomy, the battle between Scuti, the former champion, and Stephenson, 2-18, the new record holder. This is not just a comparison of size. It is a journey into the limits of stellar evolution, the power of modern space science, and the humbling reality of how small we are in the face of cosmic grandeur. Let us start with the former king, Scuti. Discovered in the 19th century at the Bonn Observatory in Germany, this star was catalogued as a faint variable star in the constellation Scutum, the Shield. For more than 100 years, it remained little more than a blip on astronomical charts, a distant red star pulsing softly in the galactic dust. That all changed in the early 2010s, when astronomers used advanced ground-based telescopes and early Gaia satellite data to calculate its true dimensions. Early measurements painted a staggering picture. Scuti had a radius of roughly 1,708 times that of the Sun day. To put that in perspective, if you replaced our Sun with Scuti, its outer atmosphere would stretch past the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter, entirely stopping just short of Saturn's orbit. Its volume was estimated at nearly 5 billion times that of the Sun, meaning you could fit 5 billion suns inside this single star. For years, this made Scuti the undisputed largest star known to humanity, an icon of cosmic excess, featured in every space documentary and astronomy textbook. It became the gold standard for stellar gigantism, a symbol of how far stars could swell in their final stages of life. But astronomy is a science of revision, not permanence. As the European Space Agency's Gaia mission released more precise parallax data measurements that determine a star's distance from Earth, astronomers realized they had made a critical error. Scuti was not as far away as previously thought. Earlier estimates placed it at nearly 9,500 light-years from Earth, but refined Gaia data puts it at just 5,900 light-years. Distance is everything when calculating a star's radius. A closer star appears brighter and larger, so miscalibrating distance leads to overestimating size. With the corrected distance, Scuti's radius drops dramatically to between 755 and 909 solar radii. Its volume shrank to less than 1 billion times that of the Sun, knocking it out of the top 10 largest stars entirely. The king was dethroned, and the hunt for a new champion began. That champion would come from the same corner of the galaxy, a star, hidden in a dense cluster of supergiants, Stephenson 2-18. Stephenson 2-18, often shortened to STEET 2-18, was discovered by astronomer Charles Stephenson in the 1960s, buried within the Stephenson 2 open cluster, one of the Milky Way's most massive star clusters, home to at least 26 red supergiants. For decades, it was overshadowed by its more famous neighbor, Scuti, until modern high-resolution spectroscopy and infrared imaging revealed its true power. Located roughly 20,000 light-years from Earth, deep in the constellation Scutum, this star is not just a supergiant, it is a hypergiant, pushing the very boundaries of what stellar physics says is possible. The latest and most widely accepted measurements give Stephenson 2-18 a radius of about 2,150 times that of the Sun day. Let that sink in for a moment. If we placed Stephenson 2-18 at the center of our solar system, its photosphere, its visible surface, would extend far beyond the orbit of Saturn, swallowing every planet, up to and including Saturn itself. Light, which travels at 300,000 kilometers per second, would take nearly 9 hours to circle the entire star. Its volume is an astonishing 10 billion times that of the Sun, double the peak volume once attributed to Scuti. This makes it not just the largest known star, but one of the most luminous too, shining with the intensity of more than 430,000 suns. To stand on a hypothetical planet orbiting this star would mean bathing in a flood of light and radiation, unlike anything in our solar system, a sky dominated by a searing red sphere that fills the entire view. To understand why these stars grow so large, we must look at how red supergiants are born. Both Scuti and Stephenson 2-18 began their lives as massive main sequence stars, with masses between 20 and 40 times that of the Sun day. These stars burn hot and fast, fusing hydrogen into helium in their cores at a furious rate. Unlike our Sun, which will live for 10 billion years, these massive stars run out of core hydrogen in just a few million years. When hydrogen is exhausted, the core collapses under gravity, heating up until helium fusion begins. This sudden burst of energy pushes the star's layers outward, inflating the star to hundreds of times its original size. The star cools as it expands, turning from a hot blue or white star into a dim red supergiant. This is the late life crisis of a massive star, a delicate balance between gravity pulling inward and nuclear fusion pushing outward. Both Scuti and Stephenson, 2 to 18, are in this final unstable phase, shedding huge amounts of mass into space in the form of stellar winds and gas clouds. Scuti loses mass at a rate of nearly 600 thousandths of a solar mass per year, shrouding itself in a thick cocoon of dust that makes precise measurements so difficult. Stephenson, 2 to 18, is even more unstable, its outer layers convulsing as it fuses heavier elements in its core, heading toward an inevitable cataclysm. One of the most fascinating parts of this story is the science behind measuring these giants. You cannot simply point a telescope at a star and measure its radius directly. Stars are so far away that they appear as point sources, even to our most powerful telescopes. Astronomers use a combination of parallax for distance spectroscopy, for temperature and luminosity, and stellar evolution models to calculate radius. For Scuti, the problem was twofold. Its distance was miscalculated, and its dusty envelope blurred its true outer edge. Stephenson, 2 to 18, presents an even greater challenge. It lies in a crowded cluster, surrounded by other bright supergiants and thick interstellar dust that absorbs light. Early measurements missed its true size because it was lost in the glow of its neighbors. It was only with the James Webb Space Telescope's infrared vision and machine learning data analysis that astronomers could isolate Stephenson, 2 to 18, and measure its parameters with confidence. This is a testament to how far space exploration has come. What was once impossible with ground-based telescopes is now routine with space-based observatories, rewriting cosmic records, one star at a time. Let us put their sizes into human terms to grasp the scale. Our Sun is a sphere, roughly 1.4 million kilometers in diameter. The Earth is just 12,742 kilometers across a tiny speck next to the Sunday. Scuti, even at its revised size, is still large enough to fit nearly 800 million Earths inside. Stephenson, 2 to 18, it could hold more than 1.3 quadrillion Earths. If you shrank the Sun to the size of a standard basketball, Stephenson, 2 to 18, would be a sphere nearly 2 kilometers wide. These numbers are not just abstract. They reveal a fundamental truth about the universe. Size and mass are not the same thing. Both stars are enormous in volume, but their mass is surprisingly modest. Scuti has a mass of only 7 to 10 times that of the Sun, and Stephenson, 2 to 18, is estimated at 20 to 30 solar masses. Their low density means they are like cosmic cotton candy, huge, fluffy, and incredibly sparse. The outer layers of these stars are so thin that you could fly through them without feeling resistance, a far cry from the dense fiery core, where nuclear fusion rages. The fates of these two giants are equally dramatic, and both will end their lives in the most violent explosions the universe can produce: core collapse, supernovae. For Scuti, the end is less than 10 million years away, a blink of an eye in cosmic time. Its core will continue fusing heavier elements, from helium to carbon, oxygen, neon, and finally iron. Iron cannot be fused to release energy, so the core loses its outward pressure. Gravity takes over, and the core collapses in a fraction of a second, triggering a supernova that will outshine an entire galaxy for weeks. The core will either become a neutron star, a city-sized sphere of matter, so dense a teaspoon weighs billions of tons, or, if the core is massive enough, a black hole. Stephenson, 2 to 18, faces a similar fate, but on an even grander scale. Its extreme size and mass mean its supernova will be one of the brightest and most energetic events in the Milky Way in recent history. After the explosion, its core will almost certainly collapse into a black hole, leaving behind a nebula of gas and dust that will seed new generations of stars and planets. In death, these giants give life. The heavy elements forged in their cores, carbon, oxygen, iron, are the building blocks of planets and of life itself. We are made of stardust from stars just like these. This showdown between Scuti and Stephenson, 2 to 18, teaches us a vital lesson about science and exploration. The universe is full of surprises, and our understanding is always evolving. What we accept as fact today can be overturned tomorrow by better data, better tools, and better thinking. Scuti was not a mistake. It was a stepping stone, a discovery that pushed astronomers to look harder, measure more precisely, and reach further into the galaxy. Stephenson, 2 to 18 is not the final answer either. As we build larger telescopes, like the Nancy Grace Roman Space Telescope, and next-generation, ground-based observatories, we will likely find even larger stars hidden in other galaxies, pushing the limits of what we think is possible. The Milky Way is home to hundreds of billions of stars, and we have only studied a tiny fraction of them. There could be hypergiants in distant galaxies that make Stephenson 2 to 18 look small, waiting to be discovered by future generations of explorers. We often look at these cosmic giants and feel small, but that is not the point of this story. The point is that we, a species of intelligent life, on a tiny blue planet, have unlocked the secrets of stars 20,000 light-years away. We have measured their size, calculated their life cycles, and predicted their deaths. We have turned points of light into characters in a cosmic story, a story of birth, struggle, and transformation. This is the magic of space exploration. It connects us to the entire universe, reminding us that we are part of something far larger, older, and more wonderful than we can ever imagine. Scuti and Stephenson 2 to 18 are not just stars. They are beacons, calling us to keep looking up, keep asking questions, and keep reaching for the stars. The next time you stare at the night sky, remember that, beyond the faint stars you see, there are giants lurking in the dark stars that challenge the laws of physics, stars that live fast and die spectacularly. The title of largest known star may change again, but the wonder these cosmic behemoths inspire will never fade. This is the story of the universe's greatest giants, a jewel for the ages, and a reminder that the cosmos is full of mysteries waiting to be revealed. Please like, comment, share, and subscribe to the channel.